After we've pre-processed our data, we then need to fit a model to it. In other words, we will estimate how much bold activity there was for each condition in each voxel in the brain. To begin, from the SPM GUI, click on Specify First Level. Note that the first field that needs to be filled in is the directory field. To keep our results organized, go to the MATLAB terminal, navigate to the sub-08 directory, and type mkdir first level. Then, double-click on Directory and select the first level directory you just created. All of the output of the first level analysis will go into this folder. Next, we will fill in the timing parameters section. Under Units for Design, select Seconds, and enter a value of 2 for the interscanned interval, which is your TR. Then click on Data and Design, and click twice on New Subject or Session to create 2 new sessions. For the scans of the first session, go to the Func directory and use the Filter and Frames fields to select all 146 volumes of the warped functional data. In other words, those files beginning with the string SWAR. Do the same for the volumes in the second session. Go back to the field for the first session. There are 2 conditions in the experiment, and both conditions occur in each run. Click on Conditions and then New Condition twice to create 2 new condition fields. For the first condition, double-click on Name and type Inc for incongruent. We will now need the onset times for each occurrence of the incongruent condition. First, go to the website github.com/AndrewYan, click on the SPM scripts repository, and click on Convert Onset Times. Click on Raw, and then right-click and save the file into the flanker directory, making sure to remove the .txt extension. From the MATLAB terminal, make sure you are in the flanker directory and type Convert Onset Times. This will convert the .tsv files into onset times text files that can be read by SPM. When the script finishes, navigate to the directory sub08/func and type the following: inc run1 equals import data, in parentheses, single quotes, incongruent underscore run1.txt, close quotes, close parentheses. If you then type inc run1 : 1, this will return the onset times for the incongruent condition of run 1. Copy the onset times, then double-click on the onsets field and paste the timing values. Click Done. In this experiment, each trial lasted for 2 seconds. If we enter the number 2 in the durations field, SPM will assume that it is the same duration for every trial. Now do the same procedure for the congruent condition for run 1, and the incongruent and congruent conditions for run 2, remembering to enter a duration value of 2 for all of the different conditions. Here I'm typing the code that you'll need to display the onset times for each of the remaining conditions. When you are done, click the green Go button. The model estimation should only take a few moments. When it is finished, you should see something like this. Now that we have created our GLM, or general linear model, we will need to estimate the beta weights for each condition. From the SPM GUI, click Estimate, and then double-click on the field Select spm.mat. Navigate to the first level directory and select the spm.mat file you just created, and then change the right residuals option to Yes. Then click the green Go button. This will take a few minutes to run. When you have finished estimating the model, you are ready to create contrasts. If we estimate a beta weight for the incongruent condition and a beta weight for the congruent condition, for example, we can take the difference between them to calculate a contrast estimate at each voxel in the brain. Doing so for each voxel will create a contrast map. To create these contrasts, click on the Results button of the SPM GUI and select the spm.mat file that was generated after estimating the model. You will see the design matrix on the right side of the panel. Click on Define New Contrast, and in the name field, type INC-CON. Then, in the contrast vector window, type 0.5, negative 0.5, 0.5, negative 0.5, and then click Submit. If the contrast is valid, you should see green text at the bottom of the window saying Name Defined, Contrast Defined. Make sure that your contrast manager looks like the figure below, and then click OK to create the contrast. Double-click on the contrast INC-CON to open the Results window. You will first need to set a few options, which are explained in more detail in the link to the ebook below. When you have finished specifying the options, you will see your results displayed on a glass brain. This shows your results in standardized space in 3 orthogonal planes, with the dark spots representing clusters of voxels that passed your statistical threshold. In the top right corner is a copy of your design matrix and the contrast you are currently looking at. And at the bottom is a table listing the coordinates and statistical significance of each cluster. The first column, set level, indicates the probability of seeing the current number of clusters, C. The cluster level column shows the significance for each cluster measured in number of voxels, or KE, using different correction methods. The peak level column shows the T and Z statistics of the peak voxel within each cluster, with the main clusters marked in bold and any subclusters listed below the main cluster marked in lighter font. Lastly, the MNI coordinates of the peak for each cluster and subcluster is listed in the rightmost column. If you left-click on the coordinates for a cluster, the coordinates will be highlighted in red, and the cursor in the glass brain view will jump to those coordinates. You can click and drag the red arrow header in the glass brain if you like, and then right-click on the brain and select any of the options for jumping to the nearest suprathreshold voxel or the nearest local maximum. To view the results on an image other than the glass brain, in the results window in the lower left, which contains the fields p-values, multivariate, and display, click on Overlays, and then select Sections. Navigate to the SPM12 canonical directory, and choose any of the T1 brains that you like. In this case, I will select the average 152 brain. You will now see the results displayed as a heat map on the template brain you selected, and you can click and drag the crosshairs as you do in the display window. If you place the crosshairs over a particular cluster and click the Current Cluster button in the results window in the bottom left, the statistical table will reappear, highlighting the coordinates of the cluster you have selected. When you have finished running the preprocessing and the first level analysis, we will then need to run this for each subject in our study. To speed up the process, we will learn about scripting, to which we now turn. After you've preprocessed and set up a model for a single subject, you'll need to do the same steps for all of the subjects in your data set. This may seem tedious but doable. We have only 26 subjects and only 2 runs per subject. An alternative, however, is to script your analysis. Just as an actor has a script which tells him what to say, where to stand, and where to move, so you can write a script that tells your computer how to analyze your data sets. This has the double benefit of automating your analyses and being able to analyze data sets of any size. The code for analyzing 2 subjects, or 200, is virtually identical. First, we will create a template that contains the code needed to analyze a single subject, and then we will use a for loop to automate that analysis for all of the subjects. To begin, from the SPM GUI, click on the Batch button. This opens the Batch Editor window, which we can fill with multiple preprocessing modules. From the top of the Batch Editor window, select the following modules in this order. This will execute all of the preprocessing steps from realignment to smoothing to model estimation. Although I'm speeding this up, the full list of modules can be found in the book chapter link down below. You will now need to fill in each of the required fields, just like we did in the previous chapters. Remember that you'll need to use the MATLAB terminal to create a folder called First Level for the first level results. At this point, you may wonder what you're supposed to input for a later preprocessing step if the required data hasn't been created yet. We use the module named file selector to assign a label to each run of functional data. Then, we use what are called dependencies to indicate that the input for the current step is the output of the previous step. For example, in the Realign module for the first session, if you click the Dependency button, you can select the option Named File Selector, Run 1, Run 2 files, and likewise for the second session. The File Set Split module is used to take a group of files that have been processed altogether, such as during the smoothing step, and split them into two separate groups for the Model Specification module. For the Contrast module, we select the Replicate and Scale option. This will replicate the contrast weights across all of the sessions for that subject and scale them in inverse proportion to the number of sessions. In this example, since there are 2 sessions, each contrast weight will be scaled to 0.5 and -0.5. The rest of the fields will be filled in just as we did in the previous chapters. The only difference will be specifying the input as a dependency from a previous step. Click on the link to the book chapter below to see details about how to fill in each field. The batch module we just created is specific to sub-01. We have used sub-01's images and timing files, and the results will only apply to sub-01. If you clicked on the green Go button, it would run all of the preprocessing and model estimation steps in one go. With a few adjustments, however, we can adapt this module to all of the other subjects in our study. First, we need to save the modules into a MATLAB script. Click on File, Save Batch and Script, and label the file Run Preproc Template. Save it to the flanker directory that contains all of your subjects. This will create a MATLAB script file that you can open in the MATLAB window by navigating to the flanker directory and typing open run preproc _template _job. To adapt this file so that it can analyze any subject on any machine, we will need to make the following edits. Replace the number 01 with a variable containing a different subject number for each instance of a for loop, and replace the username, in this case Aeon, with a variable pointing to the username of whichever machine is currently being used. This will allow us to use a for loop to analyze all of our subjects. I've already created a template script which you can download from github.com/AndrewYan. Click on the SPM scripts repository and then click on Run Preproc First Level _job. Click on Raw, right-click anywhere in the screen, and save the file to the flanker directory, making sure to remove the .txt extension. We will compare this script with the changes you will need to make in the template script you just created. First, we create a for loop that is initialized with a subject variable. This means that this new variable, subject, will use the value of each consecutive entry in the array subjects. In other words, the first instance of the loop will assign the value 01 to subject. The second loop will assign the value 02, and so on. We then use the subject variable and the user variable whenever we need to specify a path to the data. For example, the conditional statements look for whether the unzipped functional and anatomical files exist, and if they don't, the files are unzipped using MATLAB's gunzip command. Each time we use brackets to horizontally concatenate strings with variables. A line of code like this one will concatenate the strings surrounded by single apostrophes with the variables. If the variable user contains the value ayon and the variable subject contains the value o1, then the above code would expand to the following. By flipping back and forth between the script you generated and the one that you downloaded from GitHub, you can see that you need to replace each instance of o1 with the word subject and each instance of ayon, or whatever your username is, with the word user. The last part of the script we have to edit is the onset times. In this experiment, each subject had different onset times for each condition. If you already used the script in the previous chapters to convert the timing files, then you can create a variable that contains the timing information and insert it into the onset fields in the stats module. For example, the following code found around line 107 of the MATLAB script you generated can be changed from this, which contains onset times specific to sub-01, to this, in which the variable data incongruent run1 stores the onset times for the subject in the current loop, and then enters those numbers into the onset field. The code :1 indicates that only the first column of the variable should be read, which contains the onset times. When you have finished editing your script, or if you want to just use the one from GitHub, make sure to change the subject's variable to only analyze O1 and O2, since we'll be checking whether it works on a sample of the subjects before running it on everyone. You can then execute the script by typing its name. If you're using the GitHub script, for example, you would type run preproc first level job. You will then see windows pop up as each preprocessing and statistical module is run, similar to what you would see if you executed each module manually through the GUI. In the next video, we'll check the output to make sure it ran successfully. After we scripted our analysis, it seems that all we need to do is run the script for all of the subjects. Before going on, we will check whether there are any errors for the two subjects we analyzed using the script. If there are, we can fix them early on. If you examine the output of each preprocessing step by loading the images into the display viewer of the SPM GUI, you will notice that the initial preprocessing steps, such as realignment and slice timing correction, appear to have run without any errors. When we look at the output of co-registration, however, we begin to see an anomaly. Although the functional data looks normal, the realigned anatomical image looks as though the orientations have been flipped. When we look at the output of later stages, such as normalization or the first level analysis, this error has affected the functional data as well. To see why this error happens in the first place, click on the Check Reg button from the SPM GUI and select the raw anatomical image and one of the functional images. The centers of the images are very far away from each other, which causes the errors listed above. The problem is not in the data itself, and it's not an error in the script. Instead, it's a problem with the initial alignment of the anatomical image, which causes the later preprocessing steps to fail. To fix this, we need to manually set the origin. In other words, the values 0, 0, 0 for the x, y, and z coordinates. Specifically, we need to set the origin at the anterior commissure, a bundle of white matter fibers that connects the hemispheres of the brain. To do this, navigate to the sub01 anat directory and unzip the file sub01t1w.nai.gz to create a fresh copy of the original anatomical image. Then click on the Display button and load the raw anatomical image for sub01. Note that if you click the Origin button, the origin is far away from the brain. Now click and drag the crosshairs until they are on the anterior commissure. The anterior commissure can be most easily found from the sagittal view. Once you have placed your crosshairs in the vicinity of the anterior commissure, you should also see a thin band of white matter in the axial view and the coronal view. Take a look at the numbers in the millimeters field. These are how far away from the origin the crosshairs are along the right, left, anterior-posterior, and inferior-superior axes. We will use the fields found below, right millimeter, forward millimeter, and up millimeter, to manually shift the origin to the anterior commissure. To do this, enter the opposite of each number in the millimeter field with its corresponding field below. We will now click the Reorient button to permanently set this new origin of the anatomical image. When you click on the Reorient button, you will be prompted to select any images to reorient, with the anatomical image already selected. Click Done, and also save the reorientation matrix. Now check the initial registration again between the anatomical and functional images. The centers of the images, while not perfectly aligned, are now in a much better initial position. This increases the odds that co-registration, and by extension normalization and first-level modeling, will succeed. Once you have reset the origin for each subject, rerun the pre-processing script that we discussed in the previous chapter, this time including all of the subjects. Note that if the subject has already been run for some of the subjects, such as sub 01, sub 02, and so on, at the model estimation stage, you will be asked whether you want to overwrite the currently existing statistical output. You will either have to manually select OK, or, beforehand, delete the currently existing first-level directories. The other preprocessing output will be overwritten. Once you have analyzed all of the individual subjects, you are now ready to perform a group-level analysis, which we will cover in the next video.